Hey there folks, Mr. G here with another educational video. This time, following up on what we did last time with rational expressions, multiplying and dividing, we're going to go through adding and subtracting. And this has the exact same rules as we would have with regular fractions. If we have two fractions with the same denominator, what we do is we keep the denominator the same and we add the numerator to get our answer of 7/3. If our denominators don't match, we need to make sure that they do. The way we change these fractions is by multiplying the top and bottom by the same value. If we multiply the top and bottom of this fraction by 5 and this fraction by 3, now our fractions have the same denominator and we can use what we did before to get our final answer. Just like with regular fractions, we start by making sure our fractions have the same denominator, then we add or potentially subtract the numerators, keeping our denominator the same. Let's take this for example. As we can see, our denominators are the same, so all we have to do is add or subtract our numerators. Our denominator is going to stay the same. Now be careful, when we have a minus sign out front like this, we're subtracting this whole thing, both parts. So this negative sign is going to go on both parts of our numerator, giving us this result. We can simplify our numerator. Now you might think that this is our final answer, but remember, we want to make sure that our fractions are fully reduced. We can actually factor our denominator here, it's a difference of squares, and cancel out on top and bottom to get our final answer here. If you stopped here, this is not fully simplified, this is our fully simplified answer. How about this example? We look at our denominators, and they're definitely not the same, so now we want to think about what we can do to make sure our denominators are the same. First of all, this one has an x cubed, this one has an x squared, so on this side we're going to need to multiply the top and bottom by x in order for the x's to match on our denominators. Next, our least common multiple of 6 and 9 is 18, so if we multiply this top and bottom by 3 and this top and bottom by 2, we can get the same denominator, like this. And from here, we can just subtract our numerators and get this result. Now you might be tempted to say, oh, we've got an x squared up here and an x cubed down here. I can cancel out 2 powers of x, but this isn't the case. Because we don't have everything being factored on the top here, and in fact there's nothing to factor on top here, we can't cancel out these x's. That would be like having a fraction like this and saying, oh, we can cancel out these 12s and we'll get -3/1, which is definitely not true. So don't cancel out our x's in this case. Let's think about this question here. We can see right off the bat that these denominators are definitely not the same, and we might be tempted to just multiply each denominator by the other denominator. So we would multiply the top and bottom of this by x squared plus x, and then do the same on the other side, multiplying by 1 minus x squared. But this is going to result in some absolutely huge polynomials and lots of different terms, and there's a way to be a little bit more clever. First off, this polynomial right here has our x squared as negative, so let's flip that around to avoid problems in the future. X squared minus 1 we can factor as a perfect square, and for our denominator over here we can factor out an x as well. Once we have our expression in this form, we can see a much better way to multiply the top and the bottom by something. When we have it factored out like this, it's clear that this denominator is missing an x on the top and the bottom in order to match this x, and this denominator is missing an x minus 1. So multiplying in this way, we can much more easily get matching denominators without having to deal with a bunch of cross terms in multiplication. Now that our denominators match, we can add our tops, and I'll expand this part out here, simplify the top, and we get our final answer. There's no more simplification that we can do, and you could multiply out this bottom here, but I think this is totally fine. Now what if we had something where we had both addition and multiplication? In this case, we need to remember order of operations, in other words, bedmass, which tells us that this multiplication comes before our addition here. If we want to multiply these two fractions, remember we factor everything first, cross-reduce, and then multiply. There's nothing we can do to the top part of our fraction here, but this bottom part we can factor. We want two numbers that multiply to 2, add to 3. 1 and 2 work, which tell us that our factors are x plus 1 and x plus 2. Over here, we can factor out a common factor of 3, and here we go. We see we've got a factor of x plus 1 on the top and the bottom we can cancel out, and now we can multiply through with the rest. We want to make sure that we leave our parts factored, because this will be more helpful when we do the addition afterwards. Because recall that for addition, our first step is to make sure our denominators are the same. So let's factor this and see if they are in fact the same. So two numbers that multiply to give -10 and add to give 3 would be 5 and -2, and as we can see, our denominators aren't the same. But we can make them the same by multiplying this fraction on top and bottom by x plus 2, and this fraction on top and bottom by x minus 2. Once they have the same denominators, we can add the numerators together. Don't forget these factors that you multiplied by, and now we have to slog through a little bit of algebra. So I'll multiply these two factors and these two factors together. Once we have the top all multiplied out, we can simplify, and we'll get this. Now you might think we're done, but we've got one more step of simplifying because this top part can be factored. Using the numbers 15 and 2, this is a hard trinomial. We factor the first two and the last two. We've got a common factor at the start and the end, and now we have our factored form of our top, and we can in fact cancel some of these factors to get this as our final result. That was a tough one for sure. Our final example for this video is this one right here. Now I know this looks really scary. We've got fractions inside fractions. And this has a fancy name, it's called complex fractions. But remember, this line right here is the same as division. So another way that we can write this is like this right here. Keep in mind with complex fractions, we have to simplify the top and the bottom first before we divide. Now you might be tempted to say, oh, we've got division here, so I can just flip these two fractions individually. But that's not how it works. We have to get this as a single fraction before we flip it. If we flip each one individually, it's not going to be the same. We have to make this into one fraction before we do the flip. Starting on our left side here, because remember, brackets first, we want to add these two fractions together. They've got different denominators, but we can make them have the same denominator by multiplying the top and bottom by the right polynomial here. We'll get this, which we still need to simplify a bit. We can do something similar on the other side, and we'll get this result over here. Let's clean up our two numerators. Now that we have each of these fractions as a single fraction, we can flip this and change it to multiplication. And from here, we do a bit of cross-reducing to finish off our question. Deep breath, and we're done. That's the end of our second video here. Stay tuned to our next one, where we're going to be talking a little bit about how to solve rational equations. See you then.